Good morning, chemistry students. Today's video lesson, we are actually going to be looking at standard 6F. This is where we're looking at how to calculate the pH, pOH, our hydrogen ion concentration, our hydronium ion concentration for both acids and bases. So we're going to see how these things are related to each other and how they relate back to just our normal previous acid-base experience. So hopefully you remember from either an earlier lesson or from physical science that solutions that have a low pH are acids. Acids are anything that has a pH below 7. Well, for chemistry, we're going to expand that definition just a little bit, and we're going to look at not just pH, but we're actually going to look at what pH is a measurement of. So pH is a measurement of the hydrogen ion concentration. So H plus in brackets is a shorthand way of saying hydrogen ion concentration. A solution that is acidic is one where the hydrogen ion concentration is greater than the hydroxide concentration. Now, it is important to note, especially considering we have our CFAs in this course, that hydrogen ion and hydronium molecule are interchangeable. When you put a hydrogen ion in water, it automatically makes an H3O+. I am a little bit, I guess, old school. I like saying hydrogen ion or H+ just because it's easier, less stuff to write. But you might see hydronium on your CFAs. You might see H3O+ or H3O+1 on some other examples. Basically, those two things are interchangeable. They're meaning the same thing. Additionally, when we're looking at these brackets, anytime you see these brackets, it's just a shorthand way of saying concentration. So remember, we learned in an earlier lesson in this unit that concentration is traditionally measured in molarity. Molarity is the unit of concentration that we have to use when calculating and determining pH. So, not only is their pH less than 7, but they have a greater concentration of hydrogen ions. That's what makes it acidic by definition. So if we're looking at a typical solution at room temperature, the hydrogen ions concentration must be greater than 1.0 times 10 to the negative 7. We're dealing with really small numbers, but in order to be acidic, we have to be larger than that. So in order to be larger than that, we're talking about negative exponents. That means my exponent is less negative. So 10 to the negative 6, 10 to the negative 5. Any of those would be considered an acid. So this is an actual example. I've got hydrochloric gas. So we have HCl gas. When we get it fed through water, it's going to form hydrogen ions and chlorine ions, and it's an example of an acidic solution. It's actually a strong acid. So just use a term that you may not be familiar with, and that is strong acid. A strong acid is a substance where all of the ions completely, or all the particles completely dissociate, completely separate into their individual ions. Our halogen acids, except for HF, are some of the strongest acids that you'll encounter. When you put them in water, they completely separate into their representative ions. Now, since it completely separates into ions, that means you're going to get a whole bunch of H+, which means strong acids have rather low pHs. They have the lowest pHs. They tend to be 2 or lower. A weak acid is an acid that doesn't dissociate completely. It doesn't completely separate into ions. It only does it partially. And in fact, it's considerably less than 100. It's like you're either 100 or you're really small. But when we're looking at those that are weak acids, their pH tends to be in the range of 2 to 7. So not equal to 7 because 7 is neutral. So with a basic solution, is the exact opposite of an acid. Bases, you might remember from physical science, they have a pH above 7. But in terms of their concentration, the hydroxide ion concentration is the one that is a larger quantities. So we have more hydroxide ions and less hydrogen ions are hydronium. Again, remember, H plus and H3O plus are interchangeable. So if we're looking at a basic solution, in order to be considered a base, the concentration of hydrogen ions is going to be larger than, less than 10 to the negative 7. So less than a negative exponent means my negative exponent is getting considerably smaller. So we're talking about -8, -9, on and on and on. We have very small concentrations of H plus because we have large concentrations of OH minus. So this is an example of a strong base. It is a substance that when I put it in water, it's going to completely separate it into its ions. Sodium hydroxide. Remember when we were learning about neutralization reactions, we saw that anything that ended with an OH is probably a strong base. So they're going to separate into those OHs and the NAs. It's going to produce a whole bunch of OHs, making the concentration of OHs go considerably higher. Now, basic solutions sometimes are also called alkaline solutions. You're never really going to hear me say that. Might see it in some online text, might see it in some other videos, but I tend to say base or basic solutions. But if you ever hear alkaline, that's where alkaline earth metals comes from, because those metals form basic solutions. So kind of going back to that. Now we do have strong bases just like we have strong acids. Same idea except for the pH is at the other end of the spectrum. A strong base completely separates. So you're going to have a lot of concentration, which means the pH is going to be really, really high. It's going to be at the upper end of the scale. So it tends to be 12 or higher. The weak bases, again, don't disassociate completely. They separate much smaller quantities, so you have a lower pH. Still got to be above 7 because 7 is neutral. So if my pH is just, 7.1, 7.2, it is a weak base. It's a very, very weak base, but it's still a base. So on that note, what's a neutral solution? Well, a neutral solution is one where the hydrogen ions, or the hydronium ions, are equal to the hydroxide ions. We have equal numbers of each. They both are going to be equal to 1.0 times 10 to the negative 7th. Exactly 1.0 times 10 to the negative 7th. If we're doing calculations and we get something like, 9.99999, round 1.0 times 10 to the negative 7th. So neutral solutions are when you have a pH that is exactly 7. That is when it is neutral. If it's not exactly 7, it's going to be slightly acidic or slightly basic, depending on is it just above or just below 7. So my hydrogen ions, that H plus, or hydronium, again, H3O plus, these two terms are interchangeable. They're going to be equal to 1.0 times 10 to the 7, 10 to the negative 7. Same thing for my hydroxide, that OH ion. It's going to have to be equal to the others. So if we were to take that pH scale and we were kind of looking at it all together, my acids are going to be on the left, my bases are on the right. The strong are at the ends, the weaks are closer to the middle, with the neutral being dead center. So that kind of puts everything in a nice, pretty neutral, nice, neat order. So, a little bit more information about it, but we haven't said how we calculate pH. So we know that pH is a measurement of the concentration of hydrogen ions. That's its definition. pH is a measurement of the hydrogen ion concentration. Well, the way it is calculated is by taking the negative log. So pH is the negative logarithm of the hydrogen ion concentration. Or, like I said, or the hydronium, Hydronium, or the hydronium ion concentration. It is the negative log. So, not that we need to get into a lot of the math of what logs are and how they work. The real big picture that we need to know for chemistry is we're hitting the log button on the calculator. And because it's the negative log, you have to remember to hit the negative button before you type the log. So you will notice that on our actual calculators, our Casios and our TIs, we're going to be using that log button quite a bit for this portion of the content. And we're actually going to be using the shift log button quite a bit. Because if I look above the log, it's going to give me 10 raised to a power. Well, that's the opposite of the logarithm. 10 raised to an exponent is how we undo logs. But back to what pH is. pH is the negative log of the hydrogen ion concentration. So remember, those brackets mean concentration. If I do not give you molarity, you would have to calculate molarity before you can get pH. My honors babies, you're going to see that. A couple examples when we get to titrations where I don't give you molarity. You got to find it. And once you've got the molarity, then you can find your pH. General students, we tend to give you the molarity just to make life a little bit easier. We give you it in molarity, so you don't necessarily have to stress it as much. But brackets is basically the same thing as saying molarity. Also, that H plus and that H3O plus, hydrogen ions, H plus, and hydronium, H3O plus, are interchangeable. I hate this. I prefer using H plus, but County gave us quizzes and tests that we have to give y'all, and they use the term hydronium. A little bit old school, but whatever. It works. So let's look at a couple examples. For example, I have a neutral solution, has a pH of, bad Miss Friends, has an H plus concentration of 1.0 times 10 to the negative 7. Okay. Well, how do I calculate its pH? Quite literally, you're going to take the negative log. All right. So since I have so many students that I know use Desmos, I'm actually going to show you how to do this on Desmos. The idea is the same for a normal calculator. It's just you actually have a log button that's very obviously placed. You can see it. They are typically near the top left side of your calculator, if you're assigned to the calculator. So in Desmos, how do I take a negative log? Well, I hit minus. That gives me my negative sign. And then I come over here to function, F-U-N-C. And when you click that, you will see log. So we are hitting log. Now that I don't need my log anymore, I'm going to come back to the main and actually type in the rest of the calculation. So I got to take the negative log of 1.0 times 10. And remember, to get something raised to a power, I got to hit this A exponent B button. It's going to give me an up thing. And notice my exponent is negative 7. So you have to type the negative. You got to type the 7. So I always like to arrow out of it before I hit enter so that I don't goof anything up. Desmos, you don't necessarily have to hit the close button. It already did the calculation for you. So notice when I take the negative log of 1.0 times 10 to the negative 7, I get a pH of 7. Neutral solutions have a pH of 7 because the concentration of hydrogen ions is 1.0 times 10 to the negative 7. So you have heard about pH before. That's old school. We have seen that before. But we also have something that's called the pOH. Well, the pOH is the negative logarithm of the hydroxide concentration. So same idea, it's just this time it is hydroxide concentration and not hydrogen. The thing about the pOH scale is in terms of the numbers, everything's flipped. So I do not advise students to look at pOH when they're trying to identify something as acid, basic, or neutral. Because the acid and the bases and the strong and the weak, everything is flipped because we're now looking at the opposite thing's concentration. But calculating the pOH is the exact same thing as calculating the pH. Take the negative log of the concentration. Now, it is interesting to note that pH and pOH are related. So I can easily switch from one to the other. And they're related by the fact that if we add them together, they equal 14. So pH plus pOH will always equal 14. That means that if I know one of them and I need to find the other, all I have to do is take 14 minus what I know, and it will give me the other one. So if I need to know pOH and I know pH, 14 minus whatever the pH is. Let's say I need to know pH, but I was given pOH. Well, 14 minus pOH will give me pH. That's probably the easier equation to use. There is another relationship for my H's and my OH's, and that's using the water equilibrium constant. It's called KW. KW stands for water equilibrium constant. But basically, KW tells me that if I take the product of both of these concentrations, so product means I'm multiplying, I will always get 1.0 times 10 to the negative 14, and this is at room temperature. We are assuming all of our reactions for first year chem are occurring at room temperature. So I could switch from my hydrogen ion concentration to my hydroxide ion concentration using KW. It's as simple as taking that 1.0 times 10 to the negative 14th and dividing by the thing that I know. But these relationships we're actually going to be using to do calculations. So I want to start with a couple easy examples. We're going to look at just calculating pH, pOH. Make certain you've got your equations either in your notes or you have your handy dandy periodic table, because if you look on the back of both the y'all's is purple. On the back of the purple and the blue periodic table, I got my purple one handy, but they are both on same setup. So back side, bottom right corner, you will see all of these pH equations. Any particular one that we could possibly need for these calculations are on the bottom right. So you don't necessarily have to memorize them. You just need to know how to use them and when to use them. So let's look at some examples. Starting with pH. So we are wanting to calculate the pH. That's what it tells me at the top. What is the pH for each of these situations? So for the first one, what's the pH if my H plus concentration, so hydrogen ion concentration, is 1.0 times 10 to the negative 11th? Well, all I got to do is take the negative log of that number. If I give you hydrogen ion concentration or tridronium ion concentration, and I'm asking you for pH, all you do is take the negative log of the number. I did not mean to do that. I meant to do this, so now I know where my thingy's going to clicky up. So, it is not hard math. Many students are fearful of it because it involves logs in scientific notation. But guys, we're not really manipulating it. We're just plugging and chugging. So if it asks for pH, pH equals, type into the calculator, negative log. So let's look at number 2, where hydronium. Hydronium is the word for H3O plus. So that is saying H3O plus in words. And that is the same thing as H plus. So it's still just the negative log of that number. So what does that look like in Desmos? Well, where's my Desmos? There it is. Okay, so let's look at this in Desmos. There we go. Now I can actually see my number. Negative sign, because I need to hit that first to get negative log. Function to get to log. Back to main to type in the rest. 6.0 times 10 to the, so that means I got to hit the A exponent B button, negative 5. So what is my pH? Well, my pH is 4.22, da 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 da. So since I have a 2-digit concentration, that means I need 2 numbers after the decimal. 2-digit concentrations means I need 2 numbers after the decimal. So my pH is 4.22. So you try, pause the video, and try the next 2. Ready? So finding my pH, well, again, H3O plus hydronium ion concentration and hydrogen ion, they are interchangeable. It's just the negative log of that number. So 2.4. Notice that since both of these items have pHs below 7, these things are both considered acids. Since my first item had a pH above 7, it's considered a base, as well as my last example. So negative log 9.0 times 10 to the negative 9. Right. So hydroxide ion concentration. Same thing. Negative log of the number. What you want to be mindful of is when you're doing your problems, make certain that you're writing the correct P. If it is hydroxide you're taking the negative log of, if it's a OH, then you are finding pOH. If it's the hydronium or the hydrogen, then you're finding pH. So that is where students get tripped up, is when we start looking at these mixed together. Pay attention to what concentration you're playing with. The math is easy. You just type it in the calculator. Negative log 1.0 times 10 to the negative 3. It's got a pH of 3. My pOH for number 2, 6.22. For number 3, negative log of that number, get a pOH of 3.70. And last but not least, if I were to take the negative log of that number, I get a pOH of 0.14. That's not right. There's a number missing. Something's not correct. Handy dandy calculator. So, negative. Of course, I could have just copied the thing from up above, but whatever. Negative log 7.2 times 10 to the, gotta have that negative there, negative 9. There we go. 8.14. I knew that was, see, I knew there was something missing. Now for these, what's acidic, what's basic, what's neutral? I wouldn't try and answer it looking at this, because everything's flipped. A low pH is a base. Sorry, let's try again. A low pOH is a base. B-A-S-E. A high pOH is an acid. I would not try and do this looking at my hydroxide concentration. I would not try and answer that question. I would take hydroxide and turn it into hydrogen. So the easier way to answer is it an acid, base, or neutral would be to turn it to pH. So pH 14 minus 6.22 gives me 14 minus 6.22 tells me that this thing has a pH of 7.78. Things with a pH above 7 are bases. So I do not encourage looking at your OH to determine if it's acidic, basic, or neutral. Some students are going to be able to do it. Most are going to goof it up. So that's how we get pH, or pOH. That's how we determine the pH. But chemistry, we not only got to go forwards, we got to also sometimes go backwards. Well, how do I undo a log? Mentioned this earlier. To undo a log, it is 10 raised to an exponent. So because it's a negative log, it's 10 to a negative exponent, because I got to keep that negative in there. So my formula for going from the pH to the hydrogen ion concentration, or the hydronium, concentration is just taking 10 raised to a negative power. So how do I do that? Well, on your Casio or your TI, you would hit either shift or second, depends on the calculator. So hit that button to get you to that other things. So shift log, second log, and then just type in whatever your pH is. So -3 for that calculator. How do I do this in Desmos? Oops, hit enter. So I'm going to use that AB button. 10 AB button, -3, because it has to be the negative pH. So my answer is 0.001 molar, because brackets means concentration. That is the concentration of hydrogen ions in that solution. So remember, this big M is telling me molarity. That H plus is telling me what ions I'm playing with. And apparently did I type something wrong? No. Oh, extra zeros. Yeah. So not going to stress this too terribly much. So don't worry too much about the significant figures, but since the pH has 2 decimal points, that means my concentration should be written to 2 significant figures. So that is why I wrote it in scientific notation to begin with, but I would accept either or I would even accept what's on the calculator. Same idea for pOH. So to undo the hydroxide concentration, to get the hydroxide concentration from your pOH, calculation's the same. It's 10 to the negative pOH. That's the nice thing, is even though these are opposite things, the math is the same. So how do I calculate that? Dadnabbit. There we go. All right. I want to know my hydroxide ion concentration. 10 raised to a negative, because it's 10 to the negative pOH. My pOH is 7.67. So 2.14 times 10 to the negative 8. 2.14 times 10 to the negative 8. So that is kind of it for pH, pOH calculations. They are all kind of centered around this. But what tends to trip students up is when it's not a straight path, when it's not just pH to pOH, or hydrogen ion to pH, or hydroxide to pOH. So sometimes we got to go a roundabout way to figure out our answer. So my next several examples are going to be some where I might have to use any of the equations that we are given. So first example, I am giving you the hydrogen ion concentration, and I want to know what is the pH. There's not one equation that will allow me to get from H plus to pOH. So what I do is I look at my formulas, I look at my equations to see what can I use. Well, if I am giving you the H plus, let's take the negative log of it. Because if we take the negative log of that, we will have pH. And that's something that's a little bit closer to pOH. So I take the negative log of that. Calculator gives me 3.60. Great. Fabulous. We now have pH. What do I need to do to find pOH? Well, we have to remember that 14 equals pH plus pOH. That means my pOH is going to be 14 minus the pH. So the pH is 10.4. This is not the only way you could solve this problem. Yes, you could go through KW. You will notice that I tend to avoid KW like the plague because I've learned from experience that many students screw it up when typing it into the calculator. So I will only use it if absolutely positively necessary. If you have a Casio calculator or if you're using Desmos, you're welcome to use KW as long as you use the fraction button. Got to use that fraction button. If you got a Casio like like a TI like I have, just avoid KW because you have to really watch your parentheses or the calculator's not going to do what you want it to do. So, no, this is not the only way to get to the answer, but it is one way. So, see if you can do the opposite. Can you go from OH to pH? All right. So, trying to do the opposite. Okay. I'm giving you concentration. Anytime you see concentration, unless you're going to the other concentration, take the negative log. So if I'm taking the negative log of this number, I am finding pOH. The negative log of that number is my pOH. It's important to note that since it's the hydroxide concentration, it's the pOH. So we haven't quite answered the question yet, but we can use that same trick that we used up above. We can use the fact that pH plus pOH equals 14. So 14 minus my pOH will give me my pH. So for my honors babies who are like going, Miss Rains, you're forgetting about significant figures. Well, that 14 really and truly is 14.00000. So there are infinite number of zeros after that. I just don't write them. So that's why I'm keeping 2 decimal places, because we round to the fewer number of decimal places when we add or subtract. I know I didn't say that earlier, but that's kind of, that's why we've been keeping those 2 numbers after the decimal instead of looking at the number of significant digits. So 2 more examples. Encourage you, pause the video, see if you can answer the questions on the screen prior to me doing it. If you can't do the first one, watch it, then try the second one. So looking at my first example, what is the H plus, my hydrogen ion concentration, if we have a pOH? And of course it's asking, is it acidic, basic, or neutral? That's kind of an afterthought. So, pOH. Well, I could go to pH, or I could go to my concentration. I could use either this equation, bad Miss Rains, not that one, erase. I can use this equation or this equation. It's just a matter of what looks easier. Well, to me, addition and subtraction looks easier. So I'm going to do that one. I'm going to use that first equation, the first top green one. Okay. pH equals 14 minus my pOH. Okay. So now I have my pH. Well, if I've got my P, it's really easy to find the concentration for that P. So since I have pH, if I take 10 to that negative power, I will find its concentration. So I am trying to find concentrations. That means I have to use this equation here in purple. I'm taking 10 to the negative pH. It is plug and chug. So 10 to the negative 10.88. Oh, I probably should have had another number there, but I'm not going to stress it at the moment. So 1.3 times 10 to the negative 11. So is this thing an acid, a base, or neutral? Well, the easiest thing to look at is the pH. So my pH is telling me that it's got a pH of 10. Well, since the pH is above 7, is greater than 7, it's a basic solution. It's a base. All right, example number 2. What is the hydronium ion concentration of a solution with a pOH of 9.18? This time I'm going to actually do what I wouldn't normally do. I'm going to use the kW just so you can see how it would be used. Again, I don't advise it. I'd probably take the same path as I did up above. But this time I'm just going to try the other way. So I have the P. That means I can use 10 to the negative to get my concentration. So I'm going to take, to determine my concentration, I'm going to take 10 to the negative 9.18. Handy dandy calculator. 10 to the negative 9.18. All right, so my concentration is 6.61 times 10 to the negative 10. 6.61 times 10 to the negative 10. Well, now that I have concentration, I can use kW. I keep calling it kW. Yes, I know it's not labeled that way on your formula sheet. It confused children having multiple equal signs, but this thing in dark blue, that is kW. That is our water equilibrium constant. So we are trying to solve for H+. Remember, H+ and H3O+ are interchangeable. They're the same darn thing. Because when I got H+ in water, they're going to automatically make H3O+. So to solve for H+, I've got to divide both sides by OH-. That means my kW expression becomes H+ equals 10 to the negative 14 divided by 6.61 times 10 to the negative 10. Because I had to divide by the hydroxide ion concentration. Divided by OH minus. For those of you who want to actually see the equation format. And my 10 looked like a 6, so let's fix that. So how do we type this into the calculator? Well, fraction button is your best friend. So Desmos, Casio folks, hit that fraction button, type in exactly what you see. 10 to the negative, bad Miss Rains, forgot to hit the AB button. 10, AB button, negative 14. That's 10 to the negative 14th. On the bottom, 6.61 times 10, got to hit that AB button, and type in negative 10. So, handy dandy calculator tells me that my hydrogen ion concentration is This is the downside of using an online calculator. 1.51 times 10 to the negative 5th. 1.51 times 10 to the negative 5th. So the only benefit of doing the other method, going through the pH, pOH, is that it's easier to answer the second part of the question. Because right now I don't really have a number that's very obvious. If it's acidic, basic, or neutral, I mean, yes, technically I could look at the H+, and I could say that, well, 10 to the negative 5, yeah, that's more than 10 to the negative 7. So we have more hydrogen ions then we have hydroxide, which means it should be an acid. Most students aren't going to be able to do that. Most students, I would suggest, take the negative log of that number. Because then you're looking at exactly the pH. And you can very easily tell with looking at the pH, is it acid, base, or neutral? So negative log 1 point, oops, dyslexic moment, 5.1 times 10, AB button, negative 5. So what's my pH? My pH is 4.8. With a pH of 4.8, this thing is an acid. So it's acidic. And no, I did not use that same method when I originally made the PowerPoint. So in the essence of time, I am only going to do 2 of these. So like I said, you can use KW. KW is very, very useful when you are trying to go from one concentration to another. So if we are trying to go from one concentration to another. But if that's not what you're trying to do, then using 3 steps might be easier and more intuitive than using that lovely pain in the tuchus equation. So in order to calculate these as acid, base, or neutral, I need my pH. I simply just need my pH. Well, first one's easy peasy. I take the negative log of that number. I'm going to get my pH. So we take the negative log of 6.0 times 10 to the negative 10, and we get 9.22. Well, that pH is above 7, so this thing is a base. But like I said, be careful, because if I'm giving you hydroxide concentration and you take the negative log of the number, so I'm looking at D here, you don't get pH, you get pOH. So you have an extra step to figure out your pH. So still take the negative log, it's not going to hurt nothing. 5.0 times 10 to the negative 7. And it tells me that my pOH is 6.30. Encourage you to label your stuff. Okay, that's my pOH. My brain can't handle flipping stuff around, so I'm going to get my pH. pH equals 14 minus 6.30. I get 7.70. Sorry, I didn't slip. I didn't round the number in the calculator. I did the whole thing. So I've got a pH of 7.7. That's above 7. Therefore, it is also a base. And no, not everything are bases. It's just arbitrary that way. So for your practice today, you've got a sheet where I'm giving you random things and I'm asking for the other 3. I'm giving you pH and I'm asking you for pOH, hydroxide, hydrogen ion concentration, and acid, base, or neutral. Or I give you that it has this hydrogen concentration, I'm asking for the other things. All of these are interchangeable. Practicing when to use which equation is the skill that we are needing. So we've seen how to use all of these equations. Now we got to practice actually picking the correct equation. That is all for today. As always, I'm available in the Meet if you need some extra help with this particular concept. If you really and truly are struggling with it and you're just like, Miss Rains, I really don't understand, come give me a visit, because I have an extra little tool in my toolbox that I can give you that might make it a little bit easier for you. That's it for today. I'll see you in the Meet next time.